Hello everyone, again Pranav here. Today I am going to explain hydrogenerator part 5. It's a continuation of 1 to 4. All other links of the previous parts are given under the description box. Before start the session, I would convey my heartfelt thanks to one of my best friends who has advised me to glorify my presentation with graphics and AutoCAD application. I shall try to follow his suggestion in my ongoing sessions. Let's start with design of stator winding. It has been recorded that about 56% of the generator failures are attributed to stator winding insulation problems. During operation, stator winding insulation of generators are usually exposed to thermal, electrical, mechanical, and environmental stresses. And failure of winding insulation depends on either single or combination of these stresses. The main root cause for insulation failures can also be categorized as 31% due to aging, 25% due to contamination, and 22% due to internal partial discharges. The insulation damages by contamination is mainly dominated by the moisture absorption within or outside of the generator. As because of hygroscopic nature of many types of insulation materials, there is possibility of moisture ingression within the insulation from the atmospheric air that is in open type ventilation system machines or from leakage of water from the coolers in closed ventilation system of the generator stator. Moisture in combination with partly conductive contamination such as oil, carbon dust, and dust already deposited on the winding insulation and ventilation paths can have to be accelerated through thermal deterioration or thermal aging of the generator stator winding insulation. One pie chart is hereby mentioned for categorization of root cause for insulation failure. Normal aging 31%, conductive contamination 25%, internal partial discharge 22%, operational abnormalities 22%. As the usual operating abnormalities, generators are always be subjected to higher than normal stresses due to temperature, voltage, and mechanical forces. The electric stress, as initiated due to fluctuation of voltages, plays an important role in insulation deterioration compared to other stresses such as thermal, mechanical, thermomechanical, etc. When the insulations are exposed to high humidity condition, natural wetting may take place. Sometimes generators face accidental flooding situation where generator windings are submerged in water. Then the winding insulation are exposed to the forced wetting condition. In such situations, the windings are dried to remove the absorbed moisture. All the influences of insulation aging parameters should be carefully examined and investigated during the design and manufacturing stages. Engineers who are in charge of mentioning specifications must have a complete overview of the machine design, their necessary performances, manufacturing processes and procedures. Insulation is one of the most critical as well as important elements to suffix the reliability of electrical machines. Any faulty design or deviation during manufacturing stage can result in a dramatic impact on the lifespan of the machine. Improvement in lifespan is directly linked to resin improvement and its using in manufacturing process to the insulation system. During manufacturing of high voltage stator windings, an intensive program of type and routine test has to be carried out to encounter any manufacturing flaw. The basic criteria of type test is to qualify the winding insulation system as suitable for its purpose. Through routine production testing, it is to be ensured that there has been no manufacturing defects and deficiencies during the coil manufacturing process. In earlier stage, using a specified insulation material of temperature class B, that is 130 degrees centigrade, the hydrogenerators were designed with lower voltage stresses, stator insulation system, and for which larger insulation allowances had to be provided in the slot area. In modern design, using a specified insulation material of temperature class F, that is withstanding of 155 degrees centigrade, stator insulation system has become much more homogeneous and less thickness, but having higher voltage stresses, and that provides much improved thermal conductivity and better heat dissipation. So, keeping the slot area same, the high voltage stator winding designer has a scope to enhance the overall stator winding copper content by between 20 to 40%. The increased copper losses can be easily handled as the cooling area within the slot has become higher due to application of thinner layer of insulation with improved thermal dissipation. The main aspect of the HV coil design for hydrogenerators is therefore reduction of copper losses and optimization of thermal characteristics for better dissipation of heat losses. The hydrogenerator rotor of salient pole construction, having with large variation of magnetic permeance in direct axis and quadrature axis, and a concentrated nature of rotor field pole windings, there must be a sensitive intervention during design of the rotor pole phase. Design criticality includes rotor pole phase shaping for sinusoidal approximation of rotor magnetomotive force, that is MMF, and adjustments of damper winding relative to the slotted periphery of stator core for reduction of the slot ripples. The hydrogenerator operational speed is relatively slow and necessarily large number of rotor poles. So, the stator winding has also to be constituted with large numbers of pole phase groups, and for which the stator winding magnetomotive force formation, that is MMF formation, would have the possibility to become a distorted one. To achieve as close to a sinusoidal output waveform, necessary designing measures must be implemented. While designing stator winding, the main focus must be therefore on the better optimization of output waveform as sinusoidal as possible and effective reduction of harmonics. As hydrogenators are preferred to use for peaking duty, which supposed to be rapidly loaded, then significant radial electromagnetic forces may be exerted on the winding sections embedded in the stator slots. Because of significant difference in coefficient of thermal expansion, the copper winding will be warmed up much faster than the surrounding iron part, that is, the core slot, due to which there would have been appreciable differences in axial and radial thermal expansion between the copper conductor and the stator core, imposing significant compressive stresses on winding insulations and possibly causing insulation creepage. Creepage is the shortest distance to another conductor along the surface of the insulating material. If there is any possibility of looseness in the winding slot section, then electromagnetic forces as developed in the slot will cause radial movement or vibration of winding at double frequency, causing rapid abrasive wear between winding insulation and stator core laminations. The slot wedging system, radial slot strips and slot section side packing are thoroughly designed as the slot support system to prevent in slot winding vibrations. The slot section grounding system should have to be ensured for prevention of in-slot partial discharges. Winding configuration. The stator winding is a conventional lap wound design to provide reliable performance and getting improved lifespan of the machine. The winding insulating materials are all designed and tested at class F temperature grade, that is 155 degrees centigrade. Now let us discuss about performance-oriented differences between Baroon and wire-wound machines. 1. Baroon machines differ from wire-wound designs, where the copper windings of the stator are composed of individual copper bars rather than wire bundles, which are then wrapped with insulation and are laid in the slots on the inside diameter of the core in a precise mechanical configuration. Number 2, there are generally two bars, one on the top and the other beneath, in each slot and are held in place by wedges that slide into the top of the slot. In order to lay the bars into the slot, the opening of the slot has to be quite large as compared to wire-wound machines, as the required insulation space between the individual bars is more than between the wires in a wire-wound machine. Number 4, for the same machine rating, this criteria leads to some of the most important differences in performance between Baroon and wire-wound machines. In case of Baroon machines, extra amount of insulation is to be added where the difference in voltage between the conductors is greater. The greater levels of insulation in the Baroon design tend to make it more difficult to cool the machine. In a wire-wound design, the windings are usually preformed wire bundles which are inserted into the stator core, often by machining processes. With wire-wound design in number 8, the slot opening is significantly smaller and individual windings are composed of much smaller cross-section materials, and insulation space between the individual wires is less than that of the Baroon coils. So, number 9, so far the physical characteristics of the more compact wire-wound machines result in lower harmonic distortion in the voltage produced. In general, number 10, the larger air gap and slot opening size of the Baroon machines will result in greater levels of inherent voltage waveform distortion, particularly at higher frequencies. Number 11. So, Baroon machines will typically exhibit poorer waveform quality than wire-wound machines of similar ratings. Number 12, since the slot opening is less in the wire-wound design, the magnetic circuit that exists more efficiently between the rotor and stator. 13. These two factors lead to better overall performance of the wire-wound design for similar material content. Number 14. Usually, the reactance of a wire-wound machine will relatively be lower than those of similar sized bar-wound machine, reflecting this physical distance. 15. Having greater quantity of raw material, the bar-wound machines are typically more difficult to assemble. Number 16. These factors altogether lead to higher cost per kilowatt for the Baroon design and greater difficulty in acquiring replacement parts, that is, spare parts. Baroon designs typically offer better dielectric strength as well as greater mechanical strength than that of the Baroon designs, but they provide poorer performance in terms of voltage waveform quality and short circuit performance. Number 18. In general, for similar sized machines, the Baroon machine is best suited to medium and high voltage applications and cases where the loads on the machine are subjected to severe mechanical stresses. Number 19. With a rigid and heavily braced design, the impact of these mechanical stresses can be easily mitigated in case of Baroon machines. Number 20. In power generating application, the machine is always running continuously, having with frequent surge loads. 21. The surge loads result in magnetic reaction in the windings, particularly in the end turns of the stator, that tend to deform the windings and even break them over time. 22. To provide a mechanically rugged structure and getting superior quality of performance in medium and high voltage applications, it is recommended to have a better turn-to-turn insulation. 23. Globally, the range of applicability for multi-turn coil winding is up to 150 MVA and voltages up to 18 kV. 24. For bar windings, up to a rated output of 840 MVA and rated voltage of 23 kV are in service. Now, a diagram for Roebel bar and multi-turn coil. Here I have shown some copper stand insulation, turn insulation, ground wall insulation, conductive tape. Let's stop here, further to be continued at later stage. Thank you for listening the video. Kindly do like, share and subscribe. Your subscriptions would encourage to post more videos. Also share your comments or feedbacks inside the dedicated comment section. If you have any suggestions or specific topic you want, then let me know in the comment section. Thank you.